Hello, this is Subrat. Hello, this is Subrat, and we'll be starting with our session of week 10, I guess. Yeah, week 10. And before starting, I wait for some minutes for others to join, and after they join, we'll start the session formally. Thank you. Okay, so today we'll be starting with the idea of starting with the week 10 session. and it's a live session. And since no one is joining, I'll start recording this session, and hopefully you will find the recording in the. Hopefully you'll find the recording in the YouTube. So this is week 10. Give me a second. Uh, okay. So we'll discuss about generative models in this week. So there are two types of modeling in the recording is going on. Yeah, there are two types of modeling in machine learning. One is called discriminative modeling, and the second one is called generative modeling. In the discriminative modeling, we do the tasks such as prediction, classification, and all sort of those things such as regression and time series analysis. All these are discriminative models where the model discriminate between two things such as like classifying cats versus dogs and saying if this is the price of the uh, land in future or not. So those are all discriminative models. Welcoming to the generative model field, where we do not really. So the discriminative model works on the idea that the probability of y given that x given x. So it's the probability of y given x. That is, what is the probability of the data of what is the probability of a data being y given that we have the data x about we have the information x about it. Okay, so that's that. Yeah, so that's that. And the second is by coming to the generative modeling, we generally prefer designing the distribution as a joint thing. This probability of y, x, and y. So I will discuss that in the next slide. But before moving to the next slide, uh, yeah, before moving to the next slide, let's just see what these images are here. So. So they are degenerative models where we are sort of looking at uh, generating something. So here it's an example of style transfer. where in the left there is an image, and we're given the image along with the style. So in the image A is the original image, and in the image B, you see there is a small image and there is a large image. Uh, and the small image is a painting, and these all are for some famous painting by some famous artist. So what I do is that we put the image as an input, and the style as an input as well. So what the task is that you redraw the image in this style. Like if you see B, there is style given in the small image, and you take the style and you put it to the large image that is there on top, and you get a, like, you get uh, a resultant image, right? So there is that. And similarly in the image C, there is a image, there is a style. So you just put the style in that image and you get a resultant style image. And similarly, all these things. And so before talking about all these things, so this is an example of generative model. Okay. Yeah. Then coming to the like the 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 difference that I just posed now, the discriminative versus generative model. Let me reconnect my charger to it. I think I'm running out of battery. Okay. So yeah. So there are certain differences between the discriminative models and generative models, and Okay, so the discriminative models sort of learns the distance boundary between the classes. So uh, uh, you can see that the data of two clusters, and the discriminative model is learning a boundary, distance boundary that separate these two data. But in the generative model, it sort of learn the input data distribution. So, what do you mean by what do I mean by learning a distribution? So each data in this world, so each image in this world, each video, each any sort of data is a discrete thing. Like is a if you see a picture of a cat, is just an instance of one thing. So it's a discrete thing. Picture of a cat looking and a picture of cat closed with closed eyes are just two instances of a distribution. So a distribution is we can say everything. So that there is just an underlying n-dimensional distribution. The cat with closed eye or the cat with uh, opened eye, we say that these two are sampled from this distribution. Do we know this distribution? No, the distribution is unknown. But we can say that this all these images that are existing in this real world are somehow sampled from this underlying distribution. So as a part of generative model, what we are doing is that given a set of sampled images, the we're trying to approximate the distribution. We're trying to learn the distribution from which this data are sampled from, so that if we can approximate the distribution, then we can sample more points from this distribution, uh, which we require. That is called generation, right? So let's say you have data sets where the cat has closed his eye, and we have a data set we have a data where the cat has opened his eye. So, but we don't have any data or image where the cat is like half opening its eye, or let's say like closing one eye and opening one eye. So we don't have that image. So how do we get that image? So to get that image, one way is that you take all those images in the data set and you learn an underlying distribution. So since all this data are sampled from an underlying distribution, you just learn the underlying distribution, and you you just learn their underlying distribution, and then you find the point where a dog where the cat has closed its eye. Then you sample that data point from the distribution. In a sense, you have learned this distribution in a very very uh, uh, accurately. uh, you would be able to find a very close approximation of the thing that we're looking at. Again, it's not very easy to find a specific thing out of a distribution, and that's not the thing and that's not the expected result that people got when they started generative modeling. But yeah, now what they have done is that now they have achieved this. Then now you can put a prompt, Mid-Journey and all this diffusion model stuff, where you can put a prompt, and there will be image that will be generated looking at the prompt, and it will be a close representation of the thing that you want. So yes, these things are possible now, but it was not when they started with generative modeling. And second is the probability. So as I said, it's sort of tried to learn the probability of y given x. So let's say there is a data set data instance small y, and its corresponding level is data instance small x, and its corresponding level is small y. So what we're trying to do is that we're trying to maximize the probability of y being belonging to the x. That is, what is the probability of y given x? That is, you're sort of trying to maximize the probability of y given x. We're sort of trying to learn the class given the data. So we're trying to say that my class will be like dog or cat, given that the data looks like this, or the data have all these common features. Maximizing the joint probability will mean that what's the maximizing the joint probability will mean that what's the way to maximize. So is like, how do I maximize the joint distribution of x and y? It's like maximizing the per world distribution x and y, and the in the discriminative case, it was like maximizing the probability of x given y. Okay, great. So uh, okay, so how do I estimate this? So in discriminative modeling, we directly estimate the p of y given x, but in generative modeling, we estimate the p of x given y to find p of y given x using Bayes rule. So there is that. And so in the discriminative model, we cannot generate new data. Given this data, we can say that, okay, this is the class, this is the prediction, this is the regression, and like, this is the interpolation and everything, but we cannot generate new data. But in generative model, we can generate new data. And the discriminative model is specifically meant for uh, classification task, as I discussed earlier. But in generative model, so you can not use this for classification task. You can just generate new data and new stuff out of it. You cannot do any classification stuff, but you can generate things. So, and the last point is discriminative models don't possess generative properties, but generative model possesses discriminative properties. So it's just straightforward. Yeah. So the generative model possesses discriminative properties. Uh, what I meant here is that even if you learn the generative joint probability, you still learn P of I given X. You can still find the P of I given X using Bayes rule. I think that's why they said that the generative model possesses discriminative properties as well. Okay, great. Uh, so coming to the next one, like discriminative models. So yeah, so the examples. So what are the examples of discriminative versus generative models? So there is logistic regression. So in the discriminative model, under the hood of discriminative model, there is logistic regression, there is random forest, there is SVMs, there is neural network, and then there is distant trees, and then there is KNNs. In the generative models, we have hidden Markov models, we have naive Bayes, we have Gaussian mixed models, we have Gaussian discriminant analysis, we have LDA, we have Bayesian networks, and all these things. So yeah, so all these things are like sort of part of generative models. Okay. Okay. So stop Siri. Okay. So the way the slides are made is like first GAN is discussed, then VA is discussed, then AE versus VA is discussed, then AA is discussed. So what I'll do is that I'll first start with autoencoder, then I'll move to VAE, then I'll move to GANs, then I'll move to AAE. AE is adversarial autoencoder. Okay. So let me start with autoencoder first. Okay. Give me 1 second. I'll start with autoencoder. Okay, so the process of autoencoder is that the thing with the autoencoder is that uh, okay, the thing is the autoencoder is that you have an autoencoder where uh, yeah, you have an autoencoder where the encoder, so autoencoder is consisting of two things. One is encoder and then there is decoder. So encoder is typically, but not always, is typically of the safe where the size of the layers, the number of neurons in each layer will decrease with time. Okay, so with the subsequent layers. So there is encoder, and it will encode the input X to a hidden variable, hidden dimension that's called the latent space, and we name it as Z or Z, as you say. And there's a decoder which will take this latent space codes and recreate uh, the output X dash. Okay, so that's why it's called like reconstructing the input. It will auto encode, that like encode and then decode itself. So the encoder will encode X to a latent variable Z, and from the latent variable Z, the decoder will decode it. So first of the thing, like, what's the point of this? So first, let's consider the scenario when the autoencoder is not trained. Okay, so let's say the autoencoder is not trained properly. So now, if you put an image in the okay, so it will encode the image to a latent dimension, and this thing will be decoded. So when it is not, trained, um, if you put an image as an input and you get an encoding, that encoding will not. So that encoding will just be a random encoding of the image. It will just be a random encoding. Uh, yeah. So when you decode that encoding, it will give you a noisy image. It will not give you a, like, good image. Okay, so it will not give you a good sort of image. Okay, so it will not give you a good sort of image. But once you train it, so
So it will not give you a good, but so first it will be like noisy, but then you start training it. When you start training it, um, the encoder will learn to encode the image uh, as a representative space. By representative space, what I meant is that the image will be like the image will be more like the encoding will be more towards representing the image better. So if you pick a image, two similar image, the latent space. So after the training is done, if you pick two similar images, if you to pick two cat image from the and pass it to the autoencoder, and after the encoding page, you'll get latent code for both of the images. And when you compare those images, compare those latent codes, it will be also similar as well. So the autoencoder sort of learn a representation of the images in a lower dimensional space. By lower dimensional space, what I meant is that so in the all the images that you see in the real world are do not require that many dimensions to um, get represented. They can be represented with much less dimension than they have. So what you're trying to do here is that trying to find the dimension where the image can be represented without any. So there can be like you can reduce the latent space to very small, but again, if you reduce the once you start reducing the latent space to very small value, the latent dimension to very small value, it will not be able to recreate the image properly. That is, if let's say for MNIST dataset, let's say, and people have found this that let's around 16 to 20 neurons are needed in the latent space. So if you reduce that to 8 or 5, it will still be able to reconstruct by the decoder will still be able to reconstruct it, but it will not be able to reconstruct it very efficiently. That's why it's very crucial to uh, uh, very crucial to um, uh, think about this latent space very seriously and design the latent space in a way that will serve our purpose. Like I mean, if the latent space is more like is bigger, then there is no point of encoding it because like it will not compress the data much. If it is small, it will too small. It will not be able to decode properly by the decoder. So the latent space need to be just right to for this to happen. So there is a potential problem in this case. The potential problem is that so let's say you have the images of cats and dogs only, and you're trying to train an autoencoder for that. Okay. Okay. So before discussing the problem, let's just start with the discussion. What's the point of using an autoencoder? Because what autoencoder is doing is that it's sort of taking the images and it's sort of finding the latent representation, and as an output you're getting the same image back but a bit blurry, because since you are reconstructing the image uh, since you are reconstructing the image from the latent space, which is a lower dimension, the images will be little bit blurry, but that's okay. But what's the point of that? Since you are inputting the image X as an input and you're getting the same image rather distorted, a bit distorted as the output, and at the end of the day you just have two same image. So what's the point of creating an autoencoder? So there are several points of creating an autoencoder. Uh, the first one goes is that uh, so if you have an autoencoder, you can learn a representation of input data. That is, uh, let's say you want to use a smaller neural network for classification. Okay, you don't want to use very large neural network for classification. So instead of training the neural network on the original image X, you can train it on the latent space or the latent representation, uh, where sorry. Yeah, instead of training your autoencoder on the original image, you can train it on the latent code as well. So that is creating the autoencoder. Yeah, that is like using the autoencoder for compressing the data and learning smaller neural network models classifiers. And second thing is that that will benefit from this is that, let's say you want to store the data, store the images, but let's say you have very small storage in your device, but you want to store a lot of images. So if you store the larger images on your data, on your system, it might fill up the space very quickly. So what you can do in as an alternative is that you calculate the latent space representation of each image, and since the latent space representation is more than 10 times or like 20 times smaller than the original image, it will be easier to store. Okay, so it will be easier to store that in your system. So you store the latent representation. When you need the images back, you can just decode it using the decoder and get the images. So it's a way of storing the images as well, saving spaces. Another application of autoencoder is that when you want to transmit something and the bandwidth is low, so if the bandwidth is low, you can afford to load you can afford to lose certain pixels or certain quality of image. Maybe you're okay with getting a bit blurred, a bit like the reconstructed images are not that great. It might be a bit blurred or not many, like bit non-realistic per se. So you yeah, what you can do is that when those things do not matter much, but what matter is that the transmission of data from one point to another matters much, then what you can do is that instead of passing the data in its original form as an images, what you can always do is that you can always pass the images to the encoder, and the encoder will pass the images to the encoder will pass the images to uh, so the encoder will create the latent representation of the image, and the latent codes will be propagated over the network to the decoder, and the decoder will decode its the decoder will reconstruct the input, the output, reconstruct the input out of it, and which will be the output in the opposite end of the network. So now you get more speed, more bandwidth, and you can use that to send your packets, send your like images over the network. These are some of the applications of autoencoder that we see in recent days. But a potential problem came when things started to change, and people sort of focus more on the generative modeling rather than the discriminative modeling, because let's say like you have a picture of 1,000 cats, and so there, so you will be getting 1,000 different distinguished latent code for all 1,000 images, all 1,000 cats. So you will not be, so let's say you have 1,000 cat images and you are getting 1,000 z values or 1,000 latent codes for this 1,000 different cats. Okay, so since we are getting all these things, since we are getting all these cats and all these things, uh, since we are getting all these latent codes, you can see that these latent, since the autoencoder is properly trained, these latent codes will fall very near to each other. Okay, these latent codes will fall very near to each other. So let's say you want to generate a new cat. What I will do? So a common layman approach, and which also used by the autoencoder, is that you take all these 1,000 latent codes of the cats, you find the average, and you and you take the average vector that represents the cat, and then you pass that to the decoder, you will get a new cat, right? Or what you can do is that you take the cluster and you sort of find a point in the cluster. So the cluster would be like 1,000 different points that will form a cluster, and you find a point in that cluster. You just move that point a little bit towards left, right, or anywhere in one direction, and you reach at another point, and that point is your new image. Now that's a new generated image, but yeah, of that class. Since we are considering only one class, there will be a new generated image of that class. But it's not right? I mean, uh, you have, let's say, 1,000 cat images. You cannot just take average, and also the number of new cats you will generate will be limited by the number of uh, will be limited, right? And also the images you are generating is sort of depending on the input. By changing the input a little bit, and that is not cool, because you know image lies in Euclidean space. That means if you mess with the image a bit here and there, it will start to behave very differently. Okay, so that is one problem. Second problem is second problem is uh, yeah, the second problem is dealing with uh, so that is the problem. It is the problem of unique values. And second problem was dealing with what was that? Yeah, so taking the control. Okay, so let's say you want to generate the cat. So what this method will do, the autoencoder way of method doing is, you can take an average. Okay, so you'll generate one cat. If you want to generate the average again, it will not be much different than the first average. So you'll get very similar cats. Okay, even if you take data point and move here and there, it will not be interesting, because all the real world data lies in a low dimensional manifold. And if you traverse through your real data, you'll find junk. But if you travel through the manifold, or in other words, the latent space, you'll be able to find uh, meaningful data, right? So let's say you have a image of 1,000 cats, and instead of just creating a dataset of cat of 1,000 cats, then training it through an ML model, and putting it on the uh, vehicle to say that what was the task again first? Yeah. So so the task was to like create image of the cat. So let's say uh, you use this descriptive technique, and you will not be able to create um, good looking cats and real cats and distinct cats. And if you want to do it in a very controlled way, you cannot do that. So this was the problem with the autoencoder. So what variation autoencoder said is that it said that, okay, let's not learn a latent space or latent code. Let's just learn a distribution in the latent space. That is, you're not learning a you're not learning the representation of 1,000 cats. What you're trying to learn is that you're trying to learn a distribution from which these 1,000 cats are sampled. So you're sort of taking these 1,000 cats, you're sort of trying to learn a distribution which best describe these 1,000 cats. So what will happen if I learn a distribution instead of learning the pointwise distribution? Uh, the 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 profit will for me will be that I'll have a distribution. I'll have a distribution that will be in terms of standard normal, and if I have a distribution, I can just later I can just sample from the distribution to get a new data. and every time I sample, I'll be getting some new data. Since I'm not taking the mean here, so it will be all right. Okay. So that's why, like, what we did is that we sort of took this input X, we encode it. The encoded input is now two dimensions, divided into two. So we say that in the first half of the uh, Latent space Z, we are learning the mean of the distribution, the unit normal distribution, and in the not unit normal, the normal distribution, and in the second half of the latent space, we are learning the standard deviation of the normal distribution, and the Z is not directly associated with the not directly associated with the what do I say? Not directly associated with the input X. It's just a sample from the distribution that we're trying to learn. Okay, and that G will be decoded. So every time you put an image while training, it will update. So every time in the input, sorry, in the training, it will try to figure out this the parameter that will give rise to mean and standard deviation of different distributions, and for every image, so you can just you know learn a latent distribution and from which you can sample. And so the latent distribution that is there in the mu and sigma is called something. Wait, let me guess. Yeah, okay. So the distribution that is there on the on these red boxes, the mu and sigma that you're trying to learn of a distribution is first, like, you have to do a KLD between that distribution and the standard normal, because since every data is sampled from the normal distribution, you need to validate that the distribution that you have learned is normal. Okay. Once you do that, you get the Z, and the decoding process is the same as autoencoder. So there is that. And once you train that, after training, there's two things you can do. You can still do the reconstruction one. That is the goal number one. What you can do is just pass the image. The image will get a corresponding mu and sigma. Then sample from the distribution. Then you sample from the so sample from the distribution, and now you draw your you sample from the distribution, and then you decode it to get your images, right? So it's like that. It's like saying, instead of learning a specific code for specific people, which will be very long and tiring, what you can do is that you find a small group of people and explain them how this is, and everything else will be taken care of by, like, yeah. So instead of finding specific codes for different input images, you find distribution that represents specific inputs. Then for the latent code, you can sample from this. When you learn this distribution, you can sample from this, and you can generate the images. So you can generate the reconstruction ones. There's the one goal that I'm talking about. The second goal is that uh, generating new images. That is, let's say you would learn the distribution that is underlying. Uh, yeah, let's say you learn the distribution that is underlying a data set. Okay. Now, what you want to do? You want to generate. So now you have mu and sigma and everything for that model. Let's say VAE for variation autoencoder. Now what you want to do is that you want to generate a new person space. Now what will you do? Like in the Lakme, or like uh sorry, not from left, like, so, yeah, that is application number one. The application number two is like you want to generate a new data out of nowhere. So there is a distribution, and you just want to generate a, let's say let's say you have 1,000 cat images, and you have used various autoencoder to learn the distribution of the cat images. Now, you have a distribution that represent the cat images, and now you want a new cat image. What you will do? You can just directly sample from the cat image distribution without worrying about the quality of the cat and everything else. Because since you are learning a distribution, you now have the approximation of the underlying distribution that the cat possesses. And if you have the underlying distribution, you can just directly sample from it to get a new cat, and it will most probably not be same as the images that you have in your repository. If you have say, millions and billions of similar cat images, then it's possible that it will generate a very cat that looks very similar to the other cats. But given the diversity of the cats that you have in your hand, and constraining it to not generate something like this, it might be able to generate a cat which is much more and way more different than the one that you see now. Okay, so this is the power of like generating generative model where you generate things out of random noises. So for reconstruction, you use encoder and decoder together. For generation, what you can do is that you can just take the latent code, latent distribution that you have learned, then you sample one data and decode it, you'll get a new image. If you want to generate 1,000 images out of VA, you just take the distribution, you sample 1,000 different latent codes, and you deconstruct 1,000 different points, images in the output with the decoder in the reconstruction of phase, and you'll get 1,000 different generated images. This is all about variational autoencoder that is used today. That is not used today, like it was started in 2015, and it's sort of a first stepping stone towards genetic modeling, where you can generate images by learning the distribution. Okay, so this is all about variational autoencoder and autoencoder. I will be taking a few minutes break. If you have any questions regarding variational autoencoder and encoder, you can put it in the chat or speak to me. Uh, uh, yeah, you can see the VA here actually. I did not change the slide, but yeah, you can see the VA here. It's just the same thing. Here is the input, here is the network, and you're learning the mu and sigma here. And since you're learning the mu and sigma to be this normal distribution or standard normal distribution, you just take a KLD between these two so that this will be similar to this. And you're sampling from this, and so you're sampling from this, and you're just adding this this to the normal distribution, standard distribution, and you're getting the Z, and you're decoding this Z to getting this. So what people have done is that they have tried to add additional constraint on the latent space so that they can generate better things. And some of them have what they have did is that they have added the disentangling constraint on the latent space, where the latent space that you are designing, the latent code that you are getting, the inside that latent code, the individual units should be disentangled from each other. That is, yeah, disentangled from each other. That is, each cell in the image, each cell in the latent code should represent some different thing. So if you tweak that latent code, that part of the image will be changed. So that's like if let's say you have learned a dimension or a neuron for smile, for skin tone, gender, beard, and glasses. If you sample from a place where the beard is, let's say, black or white, you'll get the similar output in the output image. So this is called disentangling VAE or the factor VAE. So it's one type of VAE, but yeah, that's the idea. Yeah, I got a question, I guess. Yeah, the question is, what's the difference in loss function in autoencoder and variational autoencoder? Good. I'll answer that question in a bit. Uh, One second, give me 1 second. Yeah, so if you look at the loss of autoencoder, it's just reconstruction loss, the L2 loss. Okay. But if you look at the variation autoencoder loss, you want the reconstruction as well as you want the distribution that you are having learning in the latent space should be similar to the normal distribution. So along with the L2 loss, you also have to have a loss that will punish the latent codes uh, formation of mu and sigma, uh, formation of mu and sigma. That is, you also want to enforce the latent code to look like the normal distribution. That's why it is also there. So, so the loss function would be the summation of the reconstruction loss and the KL divergence loss. So you can see that is in the GAN paper, I guess. Yeah. So here you can see. Yeah. So there will be a constant between. There will be like loss between the reconstruction loss as well as the loss in the latent space. Yep. Is I think that is clear. Swati. Yep. Okay. Great. So we'll be discussing now the GANs. So GAN is an interesting piece of our work that started in 2014. It's called Generative Adversarial Network. Uh, so what we're trying to learn is that we're also since it's a generative model, we're also trying to like learn the joint distribution between X and Y. Okay. So trying to learn the probability of X and Y. So since since we're trying to learn the distribution, the joint distribution. So in the GAN, there is two things. Uh, one is a generative model, one is discriminative model. So what we do is that so we first uh, so there so, there will be a latent space Z, okay, so which we're trying to model. So that will be a random latent space. The latent space will be let's say we're sampling one noise from a random normal distribution. So given that given the noise, first the step of the generator will be like a decoder. Like if you see here, the decoder take the latent space and generate an image. So the generator will be a like be the generator will like be a decoder. It will take the latent space. Uh, it will take the latent space codes and it will generate an image. And since the generator is not well trained, it will generate a random image, right? At first, the generator is not trained properly. Uh, uh, it will uh, generate a random image. So you take random image, right? So and we have also real samples from the uh, and we also have real samples from the in the we also have real samples. So what we'll do is that and there will be another component that is called discriminator. So now the generator will first generate a garbage, okay? So it will just be a random noise, and uh, and there is some real samples. So this is the first step. You take the noise, you generate something that is garbage, and we have real samples. In the second part, we'll try to train a discriminator. It is not trained initially. It is uh, in a pre-training phase. So we'll pass the image that is generated by the generator and the image that is real. Okay. Uh, uh, so 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 you got these two things, and you pass it the discriminator, and the discriminator will try to discriminate between the real image and the synthetic image. Since the discriminator is not now trained properly, it might not be able to tell you properly that if this is a real image or a synthetic image. But eventually, when you work on it, it will able to tell real image and synthetic image. So if you see, the stage one is vector Z is randomly sampled from the latent space, and stage two is generator CNN. In this case, since we're working with images, it is CNN. The CNNs will generate vector unit image. Stage three is that the discriminator CNN, which is also a CNN working with the images, classifies each image as real or synthetic based on a training data set of the real images like X. Okay, so we'll try to do the real or synthetic images. So if you see here, the discriminator is trying to find the difference between real and fake images, synthetic images. So it will improve its performance so that the synthetic image it generates will be more realistic. On the other hand, the generator will try to be like, more towards, the generator will try to be more smarter to create uh, more realistic images. So generator and discriminator signals are optimized jointly. So generator learn to synthesize increasingly realistic images, and the discriminator is, will try to discriminate the synthetic images. So since we are trying to improve this, both of these studies, both of these models, so with time, generator will generate more better synthetic images, and the discriminator will be able to, like, always be able to find the difference between that. And since generator is trying to fool the discriminator, it will create even more realistic synthetic images, which is completely indistinguishable from the real images. So in that way, the discriminator will be, and discriminator and the generator will be trained properly. And once the discriminator, the generator is, this GAN is trained, so we say adversarial network, because each one is an adversary for each other, and they try to improve each other by competing with each other. So once the model is trained, we don't really need the discriminator now. What you can do is that you can sample from the latent space directly some random vector, and we can generate a very beautiful synthetic image using generator only. Since generator is trained now, we don't care like how this trend now, we don't care about the discriminator. We just can go for the generator and generate very synthetic images out of it. Okay, this is the entire thing about GAN. I'll be discussing the loss function in a bit, but if you could not get the idea of GAN, feel free to send me uh, send me in the chat. How to visualize each feature in the latent space while the model is training. In the autoencoder, you mean, right?
Hello, yes, I want to know how we can visualize this feature in case of autoencoder or in case of a variational autoencoder.
Okay, so you want to see what is in the latent space. So what you can do is that
Yes.
uh, uh, what you can do is that there is something called t-SNE, if you know that. So t-SNE is a way to see high dimensional data in 2 dimensions. So let's say the latent code is a 100 dimension, and you want to plot it. You cannot plot
Okay.
a 100 dimension data because the real world is 3D. So you can only plot in 3D or 2D, right? So what you can do
Yes.
is that you can use this method t-SNE to just reduce the 100 dimension to 2 dimension. Okay, t-SNE is a way of representing a high dimensional data in 2 dimensions. So what you can do is that while training, you can take 2-3 pause in the training. Like let's say you're training for 10 iterations. So 10 epochs. So after epoch number 3, epoch number 6, and epoch number 10, you can save the models in these 3 models. So you'll have 3 instances of model, same model. So in the first instance, you can pass 100 images into the encoder and get 100 latent codes, the corresponding latent codes. Then you can take this 100 corresponding latent codes and pass it to the Tisney algorithm. It will give you 100 two-dimensional points, and if you have a two-dimensional point, you can just plot it using matplotlib, using plt dot scatter plot. Okay, so you do that for the instance model number 1, that is that you did in between training. So you use the term in between training, right? So if you're training like after the third epoch, you can plot this. After the 5th epoch, you can plot this. After the 7th epoch, or 10th epoch, you can plot this. And as you'll see that when you train the model, the encoding that we are learning will be clustered around the same class. Like if you're looking at let's say cats, so cats will have, if you're looking at cats, so cats will be clustered in one, like cats will be clustered in one, cats will be clustered in one cluster, and dogs will be clustered in one cluster. I'll just show you like how it will look like. I have one. Okay, so this is another work, but I plotted the latent code of MNIST, and this is how it looks like. Okay, so this is the comparison of two different things. So this is like MNIST data, that is after the model is autoencoder is properly trained, I just pass the images to the autoencoder, and I got back the latent codes out of it. So I got back the latent codes out of it, and you can see that all these latent codes are clustered. Like I used different color for different class, so there are some here and there happening between the points, but you can see it is fairly clustered, like 10 different classes with 10 different colors. So what I did is that, so in my work, I applied another constraint so that they will be more distinct from each other. Like you can see all these things are very distinct, far from each other. But that's not the point. The point is that you can visualize like this using Disney. Okay.
Yeah, but
That is.
I want to know, like, see, cat has different features, right? Eyes or whiskers and all that stuff. So I want to understand, like, which feature is so. And not only differentiation in cats and dogs, but I want to understand what all features are learned during the training process. Is that possible?
Oh, so that can be, that is like, that's the work of, if you want to visualize that, then you can, what you can do is that you can take the filters that is coming out of the CNN. You can visualize that. So not the filters, I would say the intermediate outputs of the filters. Like you apply a filter, you get an image, right? In each layer of CNNs, you can apply that to a classification network where you can see that, okay, so which part of the image is responsible for giving this classification output. But to be honest, like in autoencoder, since we're not learning something that is specific for classification, or specific to assigning a class. In autoencoder, we're just learning it's just the representation. I don't think you'll get much visualization as such. If you just take the CNN classification network and visualize the intermediate layer, I think in week 3 or 2 it was discussed that how to visualize the intermediate layer of a CNN. If you do that, you will get some interesting output and interesting results to look at. I think if you refer to that week's video, I think Professor has mentioned how to visualize these things.
Okay, so you mean to say if I just take the encoder output and try to visualize which all features are getting learned by the model. So if I just if I make encoder and decoder separate and just is that possible to just keep those two networks separate and understand which all features are learned by encoder?
Yeah, I mean, not features are learned. I would not say which all features are learned by encoder. I would say that uh, uh, how the encoder is representing the images in the latent space. Yeah,
Okay, it
you
will
can
just
say.
give the representation.
Yeah, it will get the.
Okay,
It will just give the representation, and it can say that. Yeah, you
representation.
can.
Okay.
You can learn that what caused a cat's representation to look like this and what caused the dog representation to look like this. That means the representation that you'll get for two cats will be much different than the representation you will get for a dog. So yeah, you can visualize the intermediate layer of autoencoder to see which sort of part sort of was responsible for creating this cat's representation, which sort of part is responsible for dog's representation. And also, like if you take the two representation of two different cats, it is expected to be similar and nearby.
Okay, got it.
Yep.
Thank you.
Yep. Yeah, please mute if you have asked your questions. Okay, so yeah, so the loss function of GAN. So the loss function of GAN looks like that. Like you first need to put a loss on the generator. So there is a generator loss and then there is a discriminator loss. So the generator loss says that you take so it's like the generator loss is embedded inside the discriminator loss. So what you do is that you take the input Z and you pass to the generator Z, I mean Z, and you pass to the generator Z, you get the generated output ZZ, okay? And you pass the ZZ and the real X to the discriminator, and you get you get a prediction score for these two inputs. That is, so if you see, so there is the expected, so expectation is just mean. So mean of all the real images that are passing to the model, the passing to discriminator D, and if you recall, so for binary classification we use binary cross entropy, and this formula is just the binary cross entropy formula, where the input in one case is the real image X, and in another case the input is the fake image that is generated by the generator. So you see, in the place of X, we're putting G of Z. So that is the output that we're getting from this. There's a like an output that you're getting by passing the latent code to the generator. So once you do that incrementally, you'll minimize the loss of both these networks, and it will eventually compete against each other to form a better image. Here is a list of here is a list of things. I mean, so after after like the invention of GAN, there are a lot of GAN paper that started flowing in the conferences and journals where people talked about how to tweak the initial GAN's algorithm and the loss function to get better at it, to generate better images and all these things. So, when we talk about this, we generally talk about the GANs and a few of them, conditional GAN, WGAN, and all these things. Since we'll not go into the details of all these techniques, I will prefer to stay away from it. So, but you can definitely check it online, like for the different sort of GAN functions and GAN loss functions and everything else. So, coming to the next one, so I already discussed all these things. Coming to the last part is the diffusion model. So, if you have heard about the recent advances in the computer vision and the generative model field, so you must have learned about the recent OG thing that is going on. It's called the Midjourney, or generating images out of text. Like you put a text prompt, like generate an image of a goat taking selfie. So if you just put that image, a goat taking selfie on a moon, you'll generate that image. So all these things are based on this idea of diffusion models. So initially, when the diffusion model started, it was not very stable, and but with time, it has been stable. Uh, with time, like people have researched and made it stable. So what is we call stable diffusion. I'll just show you a demo. So let's say there is a example of stable diffusion. Let's say I say a goat is taking a shower, and if I hit generate, it's showing error. I think I need some sort of access for this. Shower. Let's put the style to none. Generate. It will take some time to generate. Still processing. Yep, see, goat is taking a shower. You can just ask anything. You can just put anything. A goat and a dog taking shower together in a pond. Okay. I hit generate. It will generate in 15 seconds. Yep. See, a goat and a dog. Where is the dog? Did not generate dog, but yeah, close enough. Like taking shower on a pond. It's not that good. Let's just take dog taking shower. So yeah, the point of me telling this is that the research has this front where they have created all these diffusion models. So diffusion model, what you do is that we take the image instead of encoding and then decoding it. So the GAN is like discriminant generator. The VA is like encode then decode. What it does is that it sort of add noise in each step. The image get noisy. Then it sample the image back from the noise to the original one. So it's a kind of different idea. If you learn about it, you'll get to know. So once it is trained, and when you put random noise, it will be able to get you a new image out of a sort of thing. So you can see a dog is taking a shower in a pond, dog, pond, and is getting a shower. So it's pretty like, cool. You can try this. I'll put the website on the chat. Yep. Yeah, so that's all about diffusion models. And so what I'm trying to say is that you will get this, you'll get to know all these things in detail, like once you take an advanced course in computer vision, like diffusion models and all. But for now, it's just very happy to know that, like, how we can generate these models and all these things. Yeah. So the thing is that we started our session in 5 p.m. today till the 7 p.m. But 5 to 7 p.m. Yeah. So actually, I'm attending an international conference in Poland. So it's not an evening here. It's day time, and I was taking the session during the lunch break of the international conference. So actually, I sent the mail to the NPTEL people to reschedule the meeting. They reschedule this live tutorial thing. They have not. They reschedule it. Uh, they did not. They reschedule it. That's why we don't have much time today. Like, I've been taking the class from past 1.6 or 7, like 1 hour 45 minutes. So I think I got a question like, can you tell me something more about teacher student model? So I don't have time now. So I'll discuss this type of model in the next class, because I have to run to the conference, back to the conference. I have a session there. So we'll discuss about this in the next session for Tapas, Saini. So you can check the recording. Actually, it's a big recording, like of 1 hour 45 minutes sort of thing. And we'll close the session now because the lunch time is over and to go back to the conference. But just to tell you in a few lines, the teacher-student model is a model. The teacher-student, the link of recording will be shared with the NPTEL people. But can tell something about teacher-student? Yeah, teacher-student model is something like you there is a teacher. I mean, there is a model from which the another model will learn. So teacher model will be like a more intelligent model, and the student model will be learning a similar thing, but is not very smart as that model. So I'll discuss about that model, this thing setting in the next class. So for now, we'll close the meeting now, and I'll see you next week. Just make sure to remind me of discussing teacher student model in the next class. You can leave the meeting now. We'll meet next week. Thank you.